Hello Flat Earth researchers, debaters and debunkers. Welcome to my garden, and I've set up a small experiment here with a rope and some markers on that rope to illustrate how perspective works. If we are going to prove either the globe or the flat Earth, we have to consider the instrument with which we observe these phenomena, and that is with our eyes. Perspective. Okay, I'm also going to show how looking from a two-dimensional perspective and then a three-dimensional perspective will produce different results for the angles, and therefore show you that the angles that we see the sun setting at or rising at and going over our heads on a flat Earth can and do work.
Let's first have a look though at where everything is going wrong, and this is right at the start where we make many assumptions about the ball Earth just in order to fit the geometry. Now, surveyors and astronomers will always line up their equipment at 90 degrees to the vertical, so they are looking directly ahead to the horizon, a straight, direct, horizontal line to the horizon. Now, what is done in order to represent this in the ball Earth model is we have a stick man on the left, and you can see a red line going from his eyes down into the ground, angling down. That is not 90 degrees. That's not how we would look directly ahead at the horizon, but it is represented in this way because it is said that when we see the horizon, we are seeing curvature. However, the correct way to do it would be to show the stick man looking directly ahead, and if he's on the left of the ball, then that would be angled up, and that is the correct attitude at 90 degrees. And then if you just look at the guy on the top, that's how it should be represented. And it doesn't matter how high or low you are, how big or small everything is in comparison. The point is that when we look directly ahead, we look directly ahead at 90 degrees to the vertical. So you can spin the globe any which way you like, but that stick man must always be on top. You can never be anywhere else on a circle. You are always on top, no matter where you are. So of course the Earth will always curve away down from you. And we can see that in this scenario we have the red line again showing how wrong it is, and the green line showing how it should be correctly represented. So of course the problem here with people that are just relying on geometry to illustrate how we see the horizon is that of course the green line never meets the horizon. So this is why geometry shows the red line going down, angling down into the ground. It's the only way it can be represented. But of course what we should do is put a line directly across, and you will see that no matter how low to the ground we are, or how big or small the Earth is in comparison, our direct line of sight will never, ever meet the ground. That's because the ground rises up to the midway point in our field of view. So here is our man standing on the top of the ball, and we have his line of sight going in a horizontal line, 90 degrees to his vertical, or straight down to the center of the earth, if you like. And if we just add a protractor there, we can see that the 0 is the horizon line, and that is just how astronomers look at the sky and how surveyors look at landscapes. And then if we add the sun starting at midday, almost above our heads, and going off into the distance. Now these angles here are what you'd expect to see on the ball Earth. So we can see how this is represented in timeanddate.com, where we look at Phuket on the 29th of May, and we'll have a look at how the sun goes towards the horizon, or the angle at which it goes down from midday onwards. You can see that the angle, if we were standing under the sun at midday and we looked at the sun throughout the afternoon, the angle would decrease, that we would have to look at the sun as it sinks towards the horizon. So this is an ideal and accurate representation of the angles at which we see the sun setting. So we'll just go back to that slide and have another look. You can see that at 4 p.m. the sun is at about a 20-degree angle from the horizon, and then at 6 p.m. is under 10 degrees. Of course, this is not accurate. It's just an illustration of how it is seen, but it is very close to what we saw just now in timeanddate.com. So we can see here that for the globe model, the perspective or the angles at which we see the sun go down over the afternoon are pretty much correct, no contest. But the issue here, of course, is where we have the Earth curving away from us, and it never, ever, ever comes up to the mid-level horizon line, or the horizontal line of sight directly ahead of us. So this is the problem with the globe, and hence having to have the observer looking down into the ground to say that they are seeing curvature. So let's look at one of the biggest stumbling blocks that defenders of the globe have with flat earthers. Here we have our stickman on the flat earth, looking directly ahead, 90 degrees to his vertical, which is 0 on the protractor there, just as a surveyor or an astronomer would set up their optical instruments. And we have the sun maintaining a constant height as it goes away from us: 12 p.m, 1 p.m, 2 p.m, 3 p.m, 4 p.m, 5 p.m, 6 p.m. And of course, a defender of the globe will say, well, it's impossible that the sun would actually set, because it would never meet the horizon. And as we add these lines, we can see that the angles are all wrong as well. How can we have these kind of angles justifying the flat earth when we observe something completely different? We don't see these kinds of angles when we are looking at the sun. And this is where we come across another discrepancy, a huge error in the way of thinking about the 3D perspective of the viewer when trying to illustrate that in 2D on a flat piece of paper. So here we add the green suns, representing how the viewer actually sees the sun throughout the afternoon, dropping towards the horizon. And if we add those green lines showing the angles, we now arrive at what we see is more akin to the numbers we see for the angles of the sun on timeanddate.com. But of course, defenders of the globe will tell you it's ridiculous and stupid to think that objects going off into the distance will sink to the horizon. But if you take a look at this picture, it is very obvious to absolutely anyone who looks at it that it is a 3D representation done on a 2D canvas. The way that is done is to have the vanishing point or the horizon at the halfway point, and we can see a train track going off into the distance. The parallel lines are getting narrower and narrower, and we can see the lampposts on the left and the right there starting off tall and large in front of us and going off into the distance. We know that they are all the same height, yet they appear to get shorter and shorter and smaller and closer and closer to the horizon. And we have on the ground, we have the bases of those posts also starting to get closer and closer to the horizon as they get more distant. And we can see this red line up here representing something just flying directly overhead, and it would go maybe off in a straight line, but it would still appear to sink towards the horizon. Now, usually if we were then going to illustrate a side-on view of the observer, we would just draw straight parallel lines across the page, representing like a cutaway view. But if we are to truly represent this 3D perspective, we must do it like this. Here we see at the top the lamps going off into the distance, getting shorter and shorter, and appearing to get closer and closer together as they get further away. This is a true sideways view representation of the 3D perspective from the viewer's point of view that we saw just now. And below that, what we have is how we actually see the world around us. We have the line of sight going directly out in a horizontal line from the observer, and then we have the ground appearing to rise up to that midway point, and the things in the sky appearing to slope down to the horizon line. And as you can see, the angle or the orientation I have used here is 24.5 degrees, which is the same as the axial tilt for the globe Earth. So if we put all these elements together and we show the sun represented by the green suns here heading down toward the horizon from 1 p.m. until 6 p.m. with angles that are very close to the angles illustrated on timeanddate.com, using the perspective gradient of 24.5 degrees, also known as the axial tilt of the ball Earth, we can see that the angles and perspective does work on the flat Earth. So let me just show you some of the footage I took a couple of years ago when first looking into flat Earth, and I figured if we can put the camera on the ground and see that the horizon line is still at the halfway point, then that would indicate that in our eyes the ground is coming up to the midway point, and that's what we see here in these clips. It doesn't matter how high or low you go. You might be able to see further, but our eyes always bring the ground up to the midway point and the sky down to the midway point. The horizon is always at eye level. If you can get down onto the ground this low and the ground is not going any higher than the halfway point, then it is quite clear that this is how we see the world.
Okay, what I've done here is we have the rope tied to a tree over there, and it has tape markers set at every meter along it. Okay, there we go. So if I just zoom out, take you around, it's going across the garden over here to that tree over there. All right, I'm going to show you that it's level. Okay, first thing I want to do is show you that the cord is level. Okay, as we go along, let's try it here. We can see that it's level. Okay. All right. So what's weird about this little setup is the rope is tied to the tree quite high off the ground over here, but over there it's tied fairly low to the ground. That's just because the ground is sloping. But as we can see, the rope is level. Okay. Okay. Let's imagine this marker here is our midday point when the sun is over our head. And down here I have a rope tied to a marker further along. Okay, so we have this marker here, that's one. So this is the first one along from that. 1, 2, 3, 4, 5. Okay, 5 hours, let's say 1 meter equals 1 hour, just for the sake of it, after we have had the sun go over our heads. So I'm going to put this level with the rope. Okay, and we can see the camera is at a 90-degree angle to the vertical, and we can see how high up that rope goes. Okay, but if I now come off to the side, and I will take a snapshot of this to show the...
Okay, I've just paused that so we can have a look at that. The blue line represents the angle that we were seeing when we were down on the ground over there by the base looking up, and the orange line represents the angle we can now see from this side on view. Very different.
Angle from the side at which that rope will go up.
So we'll go through all of these. The yellow line represents the horizon line, and this is at a distance of 2 meters, and the angle is 50 plus, so that's too high to see from this perspective. But if we go to the side, the angle upwards is 33 degrees, and that's a difference of at least 20 degrees from the two different viewpoints. Here we have the rope tied off at 3 meters, and the angle up to that tie-off point is 40 degrees. From that perspective. But if we look from the side, the same distance, 3 meters, but it's only 16 degrees, and that's a difference of 24 degrees, a vast difference. So here we go again at 4 meters, and now the angle up to that tie-off point is 35 degrees from this perspective. But from the side, it is only 17 degrees, and that's a difference in the angles of 16 degrees. And then we go off to 5 meter tie-off point, and the angle is 25 degrees from the yellow horizon line there. And if we take this perspective, the same distance, 5 meters, it is 12 degrees. That's a difference of 11 degrees. So these angles are decreasing and getting closer together as well. Here we have 6 meters, and the angle to the tie-off point is only 20 degrees now as we get closer to the horizon, and from the side it's 10 degrees, much less, and that's a difference of 8 degrees. Now if we go back here and look at the tie-off point at 7 meters, the angle is now down to 15 degrees above the horizon, and from this perspective it's only 7 degrees. That's a difference of about 7-8 degrees. So we now look at how many meters is this? 8 meters, and that's 13 degrees from the horizon. And if we take a side view, it is now only 7 degrees at the same distance, 8 meters. That's a difference of 4 degrees. So you can see these angles getting closer and closer together as we reach the horizon. The distance now is 9 meters, and the angle is 12 degrees. Slightly less, but the increments going down are getting closer together. And here we have that 9 meter from the other's perspective, and it's about 6.5 degrees. That's a difference of 7.5 degrees. And we have now 10 meters, and the angle is only 8 degrees from the horizon. But if we go to the side now, we can see that it's 6 degrees. That's a difference of only 2 degrees the closer we get to the vanishing point or the end of the line. And this distance is 11 meters, the last one, and it's only 7 degrees above the horizon line. And we see here that the angle is 5.5 degrees. That's only a difference of about 1 degree for the same distance, 11 meters. So there you go. If you haven't understood what this means, then I suggest you have another look and understand that the axial tilt of the globe, 24.5 degrees, in my opinion, is most likely the angle or orientation of perspective, and that is how they have pulled the wool over our eyes. Thank you.